Okay, everyone, thanks for coming. You're right with the camera? Yeah, okay, good. Yeah, thanks for coming. I was lucky enough to hear about and to go down to the 50th anniversary of the Honeysuckle Creek guys for the moon landing in July this year. And I don't know, put your hand up. Who remembers seeing the moon landing live on TV in '69? That's most of you. That's, yeah, well, I was 9, as you no doubt saw from the emails today. And I still remember being herded into a room with a black and white TV and waiting until this grainy picture came on. But it was an impressive thing at the time. But it was really wonderful to go to the 4-day weekend down in Canberra and actually pick the brains of some of the guys that operated all the equipment. And I was particularly interested in the ranging and other things. And I eventually managed to find someone that remembered all of how it worked. And it was a brilliant time. Anyway, this talk has a lot of technical stuff, a lot of numbers, and you don't need to know the numbers. I just want to give you a sense of how big an undertaking it was just to manage the communications, let alone actually building the rockets and everything else needed to land someone on the moon. The level of technical challenge was spectacular for the time. You know, we think of the moon landing as being a spectacular thing, and it was. You probably don't realise this, but it consumed 4% of the US national budget while it was running. That's how much they spent on their military. So that's the scale of programming. It employed 400,000 people around the world. So it was a large project to land people on the moon. I want to start by looking at the map of the ground stations and the orbital paths from Cape Canaveral, which is up here, Cape Kennedy. They could launch on a variety of different trajectories. So depending on how the weather was on the day, they might launch earlier, they might postpone by another day, and they had a variety of different trajectories, but they all had to fit within these basic paths because that was where they built the ground stations that could actually track the spacecraft in orbit. Now, you realise that if you're out at the moon, you only need 3 points on Earth to be able to see the moon from one of them at any time of the day. But if you're orbital, if you're only 100 miles high or 200 kilometres high, you only got limited visibility before the thing goes over the horizon. So these are the maps that show, this is the map of coverage of Carnarvon, which clearly is in a valley because there's hills that cut into the coverage from the north to the north and south. This is the Canberra site of Honeysuckle Creek, and you can see it's in a valley that runs north-south, so it's got hills on east and west. So it's got limited coverage east and west. And Tidbinbilla is another valley further over, Auroral, and then Parks, of course, is further in. But there's a lot of circles on this map. To get the ground coverage, they had the 3 main stations near Madrid, Honeysuckle Creek, and Goldstone. And at each of the 3 main primary sites, they had backup sites that had the same size of dish. So Tidbinbilla was a backup for Honeysuckle. Goldstone had another backup, and there were 2 dishes nearby at Madrid that was their primary dish. I'm going to go into details about those dishes later, but they were the sites that were used when the spacecraft was far enough away that you didn't have this problem of going over the horizon. For the orbital stuff, they also had Antigua, Bermuda, Grand Bahama, something I didn't get the name of, Ascension, Canary Islands, Carnarvon is active, Guam up here. They had a couple of ships in the Pacific. They had stuff in Hawaii. They had things in Texas. They had things on Cape Kennedy and in Goldstone. So you can see the antenna coverage charts for all of those. So that's when they were using orbital communication, they didn't need very high gain because it wasn't very far away. It was only a couple of 100 kilometres, so they were able to use VHF and UHF communications for most of it. They also used C-band radar, which is sort of 6 or 8 gigahertz, to be able to actually ping how far away the spacecraft is. So they'd know it was about to come over the horizon, and they'd start pinging their radar, and there it is, yeah, we got it, and know how far away it is now. And that gives them information about the orbital trajectory because there was all uncertainty about all this stuff. So actually being able to find out where the spacecraft was is critical to be able to compute the burns required to get the right orbital injections and things. So that's just a little picture of to go through the details. There were 26 metre dishes, 3 of them, which are 50 dB gain at Goldstone, at Honeysuckle and Fresnadilla near Madrid. And there were the 3 wing stations which had their own receivers, but typically they fed the IF through microwave links to the primary station, so they were quite close together. Tidbinbilla actually sent data up to a passive repeater on Dead Man's Hill, so there was no power up there, but they were able to point two antennas, one at Tid and one down at Honeysuckle, and the signal would be received by the antenna with enough gain to re-radiate down the other antenna and arrive at Honeysuckle, and that was the microwave link between those two sites. The NASCOM communications network was the first truly worldwide data and voice TV telecommunications network. This was really a massive undertaking. OTC guys were involved in it. Quite a number of those were there in Canberra in July. But I'm not talking about that tonight, but you've got to understand there was a lot of ground infrastructure put in place so that everyone could talk to everyone, they could get accurate timing. I'll talk about timing some more later on. In case the high gain antennas on the spacecraft couldn't be used for some reason, like the pivoting mechanism, steering mechanism failed and they had to use the omnidirectional antenna, they needed higher gain dishes on Earth to be able to get the processing gain to be able to, and the dish gain to be able to get signals to and from the moon because of the distance. And so they had these backup 65 metre dishes, which is, you'll see a picture of it in the next slide, the slide after. 65 metres is the size of parks, but they had one of those near Madrid. They had one or two at Goldstone, and they had the parks one. There's also one at Tidbinbilla now, but that wasn't put there till 73. So that gave you about 6 times the sensitivity, which meant that if you couldn't use a high gain antenna on the spacecraft, you could only use the Omni. But you could still get signals to and from the spacecraft at lunar range. So they were mostly for backup, but they're also for TV, and we'll get back on TV. Probably some of you know the story of the TV, but I'll tell you a little bit of it. There were 9 stations with 5 ships with 9 metre dishes. These dishes all had a secondary dish inside the dish, so they had an acquisition aid because the main dish has got too narrow a beam. You can't find the signal if you don't know where it is. If you don't know exactly where to point it, you're not going to hear it. So they had a smaller dish, which is an acquisition aid. The 9 metre dishes had a 1 metre acquisition aid dish at the focus point. And some of these were on ships. There's a picture of the ship later on. That was good out to about 28,000 kilometres. So they could well past the point where they would have switched over from UHF. They typically were switching over from UHF about 11,000 kilometres out. And the UHF could only reach about 20,000 kilometres anyway, so because they didn't have big enough dishes to get the gain at those frequencies.
What frequency did they switch to?
They switched to S-band. So this talks about the unified S-band system, which is that's between 2.1 and 2.3 gigahertz. Yeah. Sorry, I'm getting onto that. So the focus here is there are so many different signals, and I'll go through them later. There are so many different signals that have to be crammed onto into the communications channel, both directions, up to the spacecraft and back down again, that they didn't want to have 10 different transmitters, because that's a lot of equipment on the spacecraft, a lot of weight, a lot of development costs, a lot of things to go wrong. Instead, they focused on getting all the signals onto a single carrier and providing enough redundancy in the receivers and transmitters to make sure that if anything broke, they've still got the coverage they need. And you'll see this double redundancy in lots of places throughout the whole program. They really, because it was basically, the whole Apollo program was basically a PR stunt. I mean, there was a lot of science done, but it was for the American government, it was a PR stunt to say we're better than the USSR. And it was being done in the public eye. The USSR could afford to kill a few astronauts because the media wouldn't cover it, because the media wouldn't know. But the Apollo was done in the public eye. And so it had to be done well, had to be showing that they were doing everything they could possibly do to save, especially after Apollo 1 caught fire on the pad. But that's not the subject of this talk. They had 8 Apollo, were called Apollo range instrumented aircraft, ARIA aircraft. These were mostly for re-entry. They didn't know they couldn't get Earth-bound coverage. You saw on that satellite map there were too many places where they didn't get Like if they decided they had to come down the Indian Ocean, there's no coverage there. If they decided they're going to come down somewhere between California and Hawaii, there's no coverage there. So they had to have these aircraft to get the coverage.
There still isn't any coverage.
So the Oriah aircraft and the Oriah fleet was coordinated by, of course, Stan Anderson, who was at the event, and I spent time with him about an hour on the bus talking to him about stuff. So he ran the whole Oriah operational stuff. So all of these things had dual transceivers. So they had, for every receiver, they had another transceiver, and because they had two channels, a lot of the primaries actually had four receivers, and you'll see those in the pictures later on. So there was a lot of doubling up of hardware. This is the Honeysuckle Sight in 1969. The buildings are gone, the dish is gone. The dish still exists, it's at Tidbinbilla now. But there's a window in the back of this room. The receiver equipment was in here, and the antenna steering gear was beside that window, looking out the window, so they could actually see as he was steering the antenna, they could actually see it was really doing what he thought it was doing. And you can see the hills that are blocking out the coverage in certain directions.
Why do they have a U.S. flag there? Is that a joint venture?
It was a US facility. I mean, the US built it. It was NASA money that built it. I mean, it was Australians that staffed it and operated it, but it was very much a global program. You know, the whole Apollo thing was, there's so many countries involved in it, and the US was very magnanimous at the time in regarding it as being a human endeavour, not an American endeavour. And I think they swept us all along with their enthusiasm. So they've just recently placed some memorials saying one giant leap, one small step, one giant leap on this hill. They did that this year while we were there, opened it. And we sat on chairs that were laid out on the flat concrete slab where this building was, and had a lot of presentations and stuff there. This is the same dish. That's actually the original dish from Honeysuckle, and that's, of course, this is at Tidbinbilla, and that's a 65-metre dish, which is at Tid, which is... So there were three stations near Canberra. There was Aurora Valley, which was the one that was doing all the near-Earth orbital stuff. So they were looking at things that were spending 7 minutes from appearing over one horizon to disappearing over the other, maximum. So they had to really be quick tracking these dishes. And they, as the number of satellites went up and up and up, they were tracking them because they had to measure their paths, because the paths weren't that predictable. They had to actually measure how far away they were and calculate their orbits and send the information to NASA so NASA knew where its spacecraft were. So that was Aurora Valley. Chipton Biller was part of the deep space, so they were looking at things that are going out to Mars and places. And Honeysuckle Creek was built specifically for the lunar missions. And we had presentations and things here. Actually, these are the food tents that were there on the day. So, Unified S-band. They had multiple carrier centres. They had room for 4 carrier with all the signals multiplexed onto it, between 2.1 and 2.3 gigahertz. They ran a single carrier frequency in each direction, so there was an uplink and a downlink. And the spacecraft actually synthesised its downlink frequency from its uplink receive frequency, because it's moving quite fast at times with respect to the Earth, so it's got Doppler shift. And it wants to synthesise its own signal so that they know where to look for it. But they don't want to rely on highly accurate crystals and the like in the spacecraft, because then they don't know where to look for it anyway, because it's Doppler shifted. So if they've got range, and they've got range rate, which is the speed to or from the tracking station, and that depends on the Earth rotation as well, because the ground station's moving. So the range rate was pretty important. Then they know what the Doppler shift is to expect, and they know where to look for the signals. So it took a little bit of searching sometimes to find the signal. So they had an acronym AOS, which is acquisition of signal, which is we've found it. We're talking to it. They're receiving our signal. They're synthesising their signal, and we're receiving the responses to our. So we know we've got a two-way link. And LOS was the corresponding for loss of signal. And in the ham radio community, we talk about someone going silent key. when they die, the space community talk about LOS. So they have an LOS page with all the people from the program that have passed. On the carrier frequency returned, there was a double Doppler shift. But there was also the ranging code that was sent up was demodulated in the spacecraft and sent directly and remodulated directly onto the downlink. And so there's just under a million bits per second ranging code, which is a pseudo-random sequence. I'm going to talk about that because that was my particular fascination, which was sent up, and the same ranging code was demodulated before it even got down. It was demodulated very quickly and coherently retransmitted. So they didn't synthesize another one. It had to be phase locked to the received signal. The signal going out had to be phase locked to the received signal. It had to be exactly what they were hearing because the ranging system depends on that. Coded Doppler ranging and command CODERAC was one of the early acronyms for this stuff. So once you have the range, you can do the range twice, and you know roughly how far it's moved. That gives you an idea what Doppler shift. And once you know the range, you can then look at the Doppler shift and you say, well, it's moving at this speed towards or away from us. And you can update the range continuously from the Doppler. So as the speed changes, the Doppler shift changes, and that updates that Doppler shift then updates your estimate of the range. The S-band carrier was normally phase modulated. They only switched away from that when they wanted to put video on it. But they couldn't put video and ranging at the same time because they both use the same 1 megahertz of bandwidth around the carrier. And so the television signal was frequency modulated, so they would actually switch over to FM, turn off the ranging system, and then they could receive or send television. Actually only receive because they only have the hardware to send television from the spacecraft. So the transmitters had these two modes. And there were voice and quite a number of different data channels that were encoded onto the signal in various ways on various subcarriers, different subcarriers up and down. And I'll go into the signals on the slide after this one. So the reasons for unified S-band is, first of all, you're talking about something that's got a wavelength of about 12 centimetres, and 12 centimetres divided into the disk diameter is quite a lot of gain. If you were using VHF, you divide the disk diameter by 2 metres, you don't get even near so much gain. So the bottom line is you can actually, without having to upgrade the power of the VHF, UHF systems, you can get the required range, the required antenna gain from a smaller dish or from a less powerful transmitter. Now, I mean, to get connection, you need a total signal path that works, which means you need to use processing gain, which means you're sending at a low enough bit rate that you can average out the repetitions of the same signal to find it from the noise, which is how we receive GPS, right? My phone's receiving GPS. It's digging the signal out from below the noise because it's coming at a low bit rate, and it's frequently repeating. So processing gain, dish gain, and just transmit power. But you do better with it the higher frequency you go, because you get, as long as the dish is accurate, you get more narrower beamwidth and more gain on the dish. There's less hardware on the spacecraft because there's only one transmitter and receiver. And they reused a lot of the existing Gemini equipment. Once they got the subcarriers off for the data and telemetry and stuff, they fed that into the old Gemini equipment, and they were distributing voice and data around the globe on the terrestrial network using the same encodings that the Gemini program had used. And they already had S-band hardware that was capable of lunar range, so there was less development expense. So that was the reasons for using S-band rather than continuing with what they'd been doing previously. Signals, count them. Okay, I've mentioned Doppler. Each of the dishes actually had a quad feed point that could tell whether the antenna was pointing a little bit left, right, up or down from where it should be. And they had auto steering. So once they got the antenna pointed at the signal, it could tell if it's moving a little bit to the left and automatically move the dish to follow it. That was angle tracking. So there were 3 channels of RF coming off the cryogenically cooled amplifiers on the dish. So at the feed point, there was a bunch of there was a feed horn, four pickups fed into a mess of Magic T hybrids and circulators, adding subtracting various things to try and produce the sum signal, which is the main communication signal, and the X and the Y, which are going to become the error signals for steering the dish. The ranging codes I've mentioned only sent in phase modulation mode. The voice subcarrier in the upward direction was sent on a 30 kilohertz subcarrier, I think it was FM, and 1.25 megahertz subcarrier for the downlink. The data in the up direction was sent up at quite a slow bit rate on a 70 kilohertz subcarrier. That was commands to tell the engine, at this time, I want you to fire for 13.34 seconds, things like that. Quite critical lengths. And so low data rate, very high level of error correction and reliability on the up data link, because they want to be able to remote control the whole thing. It was like a big remote control toy to some of the guys on the ground. Telemetry was phase modulated up to 200k bits per second. That's for the downlink. That's receiving all kinds of information, not just the astronaut's heart rate and things, but basically anything I wanted to measure in the spacecraft came down via the telemetry channels, and so there's a lot of data that was multiplexed into those channels. That was on a different subcarrier, 1.024 megahertz subcarrier, which again was so the Doppler and that ranging and the angle tracking is all got these phase modulated signal bouncing around left and right, forward 90 degrees, backward 90 degrees, jumping around with all these other signals that were being encoded onto it, and they've got to extract them all again. Is we having fun yet? Television was, as I say, from the moon, television was sent from Apollo 11. Later they used different cameras. They had a real achievement. They built a camera that only weighed 6 kilograms compared to the 45-something kilograms of TV cameras at the time. And they allocated just under a megahertz worth of bandwidth to it. It actually was about 500 kilohertz worth of information. 320 line, 10 frames per second. And it was only sent in FM because it used up the whole bandwidth out to where the subcarriers were stored, which is why these downlinks were out a long way away from they were a megahertz away from the centre, because the centre was occupied by the FM of the TV. And on the ground, so that we could all watch TV, they had scan converters, which was basically a camera looking at a cathode ray tube.
And that was at Sydney Video at OTC Paddington.
They had them in a few places. I was at them at each of the primaries, but yes, that's right. So the video was actually sent into Sydney from Honeysuckle before someone had to flick the switch to get the video the right way up, because when it initially came on, it was actually upside down. The guy at Goldstone had his switch in the wrong position and didn't understand when he was being told. And anyway, they switched to Honeysuckle and they got the switch, and the video came on the right way up. And we saw Neil Armstrong stepping out onto the ladder and down onto the moon. They had biomedical signals, which was only while they were actually when they were in their spacesuits. They had heart rate and various other things that were being sent from the spacesuits to the LEM, and from the LEM were back on these phase modulated subcarriers. So this is the 1.25 megahertz subcarrier, but it was there were multiple FM subcarriers in the sort of some tens of kilohertz range that carried 7 different biomedical signals during the EVA, which is extravehicular activity, the moonwalk. They had science data, which was, again, 3 analog subcarriers with FM, and they were at these frequencies. Then they could back the whole thing off if thing was on fire, and they go back to emergency voice, which meant all the stuff got turned off and the voice was FM on the carrier itself. So you couldn't have everything else happening. You couldn't be doing ranging. If you switched to emergency voice, you couldn't be doing ranging. They had emergency Morse key, 20 words.
Okay.
Yep. Yep, they didn't ever use it, but they had it. And
did they have the capability? Did they train the
yeah, absolutely. They had 20 characters per second Morse capability.
20 characters a second.
I think that was 20. No, I'm wrong. 20 words. 20 characters per minute. It might have been. Sorry, I remember the word 20 from somewhere. When they were behind the moon, the S-band signals had nothing to bounce off, so they couldn't hear them. There was no communication when they were behind the moon. And they recorded the voice and they recorded the telemetry on tapes in the command module. And when they came out from behind the moon, they sent that at a sped up rate. So they'd replay the tape 16 times. And they could actually replay it, 32 times. They could actually play it at normal speed. And they had special subcarriers for recorded voice, recorded telemetry. Or they could play them at 32 times if there was enough signal strength and gain to be able to decode the signals. Then they could send them at high speed, so you could catch up with what you recorded while you were behind the moon. So it's an interesting challenge because the burns of the engines to return to the Earth from the moon were initiated when the spacecraft was behind the moon. They couldn't say burn now because they couldn't hear them. They had to say, we see you, we're going to lose you in 14.3 seconds, you need to do this burn. And they could send the thing up to do it automatically, but there were times, Apollo 13, they actually did manual burns. They had manual control of some of the burns for correcting the return trajectory. It's amazing they got them back. So that's all the signals, and they're all on one beam. This is.
That looks like Russell's shack.
So this is one of the primary stations. I believe this is Tidbinbilla. You can actually see the dish out here on the base of the dish, and so this is the antenna steering gear here. Your main timing equipment's over there. I'm going to talk about that a little bit. Rack of demodulators and other things. 1, 2, 3, 4 receiver controllers. So you've got 4 guys sitting controlling the receivers. You've got a couple of exciters. You've got chart recorders. Hang on, I've got these things all written down. The time standard, I mentioned. Iridium clocks everywhere. I'll talk about that a little bit.
Just make it up, please.
Teleprinter down the bottom there.
The tracking data processor, the ranging system's actually, I think it's, just a minute. No, this is the ranging system here.
Sure.
Sorry, I've got another picture from the other side. If you find this picture on honeysucklecreek.net, you can actually find the names of all the guys in these pictures as well. So,
Where is that? That's Honeysuckle Creek?
I think this is Chipton Biller actually. The photos aren't very well labelled, so I'm not certain which site's which. These 2 pictures, I've got 2 of them. One's Tid and one's Honeysuckle.
You get sorted out by someone still alive to tell you.
Well, Colin McKellar was a kid at the time, and he runs honeysucklecreek.net, so he's younger.
Who built all the radio equipment? Or who
Multiple contractors.
Yeah.
You can look at it all up. Nearly all this factual stuff came from a big PDF, 216 pages, which I read.
Right.
And it talks about all the different aspects of the system and how it was tested and how the backups worked and what all the transmit and receive modes were. And
It was like NASA engineers that decided what they wanted and wrote the specs.
Things weren't quite as formal as military procurement because it was being done in a big hurry.
Yeah.
But yes, it was all done. It was all outsourced to people that knew how to do what they needed to know how to do. So the picture's actually taken from above the receiver racks, but this is the ranging system. So these are receiver control panels, but the receivers themselves are actually under the camera. Each of the stations had to have a collimation tower. So 3 kilometres away on the hill, away from Honeysuckle, there was a reflector, and you could point the dish at it and optically sight it and know that you're pointing there, and then you could tune up the antenna steering system and make sure you know it's really pointing where you think it's pointing. So they all had to have all this collimation gear as well. Okay, the transceivers. So there were 4 channels nominally in the band, but they used 2 or 3. They actually used 3 of them for Apollo because they had two Downlink transmitters. One was used for video, so they could actually continue ranging on one channel while they were sending video on the other, which is why you saw some video from actually inside the command module as they returned. But nominally, the uplink was on 2.16.4. The downlink was multiplied in this 240 on 221 ratio, and all of the guys in their 70s, there at the 50th anniversary, oh yeah, 240 on 221. They all remembered those numbers, because that was how they knew those frequencies were being synthesized from the uplink to the downlink. And of course, Doppler shift would move it by up to a couple of hundred kilohertz either side of that, depending on what's moving towards you or moving away. They used Clifford transmitters, 20 kilowatts. There's about a 10 megahertz bandwidth. So to get them across the band, they had to retune them, which took 5 or 10 minutes. They couldn't just move the transmitter rapidly between these different channels. But you could actually run 2 transmitters out the same dish and transmit, and they were mixed together. So you could actually transmit to the command service module in orbit around the moon and to the LEM at the same time with 2 different transmitters. So you had 2 different exciters. Sorry, I think that was fed into the one transmitter, but it was fed out through the one feed, and that minimum intermodulation between those 2 signals, so they didn't mess one another up. Every exciter had a main receiver and a backup receiver, because every exciter is sending ranging codes, so it's got to have a receiver for the ranging at least. It would have a backup, so if something failed, you'll switch over to the backup. That's why there were 4 of them, because there were 2 channels being transmitted, 4 receivers, main and backup for each of the transmitters. Each of the receivers had to have 3 channels each in the RF stuff. Like what comes off the dish has already been amplified and down converted, but we haven't yet extracted the steering signals from it. So the 3 cables come down from the dish, and you've got to amplify all those and keep them all phase and gain coherent, otherwise you can't get steering information for the antenna. So those early stage preamplifiers were pretty special, very, very carefully hand-tuned. And each receiver had to have the 3 sets of preamplifiers for the 3 channels before they sucked off the information for the steering system. There was a separate receiver for the main dish, for the acquisition dish. So when they were using the acquisition dish, there's a different receive chain for that. Okay, now the big dishes were Cassegrain feeds. What that means is you've got the big dish, you've got a hyperbolic reflector out at the end, and you've got your receiver back here in the middle of the dish. So you get double reflection because the weight and the size of the transmitters and the cryogenically cooling equipment for the receive amplifiers and stuff was such that you didn't want to put it out at the focus of a 26 metre dish. So the 9 metre dishes had lesser stuff that was out at the other end of the dish, or had feeds that came off they weren't Cassegrain feed, but the Cassegrain feeds, all the big dishes were Cassegrain feed. While you're transmitting, you want to know that what you're sending is what you think you're sending, and so they had a verification receiver, a completely separate receive path, that took a sample off the transmitter output and demodulated it and verified that they were seeing what they thought they were sending. So complete system bypass backup without needing to send anything to the spacecraft to make sure that what's actually being radiated is what you think's being radiated.
Seconds, have it burn for 300 seconds.
Yeah. Okay, so that's roughly how the transceivers worked. Oh, I jumped ahead with the dish feed. So there were 4 horns on the dishes because they had to mix them together with these. So they had massive isolation between the transmit signal that was going out the antenna and the receive signal coming back down. Because although the transmitter's on a different band, any spurious from the transmitter were less than 130 dB below the transmit signal. So you're only talking a few megahertz away at gigahertz frequencies, and your spurious have got to be such that you're sending 10 or 20 kilowatts up the spout, and you've still got to hear nanowatts coming back down on an adjacent band. So there was some pretty special, obviously all done with magic plumbing. I don't know if anyone works with microwave, but you don't use wire at microwave frequencies. It's all done with feed, cavity feeds. The Magic T hybrids, I should probably have a picture of Magic T, but there was a ring of Magic T hybrids that did the mixing of from the 4 horns to produce the sum X and Y. So the sum of all 4 went down into one receiver, and the difference between these 2 and that 2 went to the X feed, and between those 2 and those 2 went to the Y feed. And that gave you steering information. The parametric amplifiers are quite interesting. Does anyone know I know this man does. Anyone else know what a parametric amplifier is? So they didn't have transistors that operated at gigahertz frequencies back then. You could build parametric amplifiers, which is varactors and tunnel diodes, which have a negative resistance or negative impedance part of the curve. And what you do is you put them in a bridge, and you balance it out so that there's no signal, and you pump in a signal on an unrelated frequency, and as the received signal comes in, it unbalances the bridge, and you get massive gain. So the single-stage parametric amplifier, the 2-stage parametric amplifier got 30 dB gain, and very low noise temperatures. So extremely low noise amplifier, but they had a circulator, which is the signals going in and going round. It's jumping out to one parametric amplifier, coming back in on the same feed, going back out the next port of the circulator to another parametric amplifier, coming back in on the same port again, and going around, coming out the 5th port, and that's the output of the amplifier. So, it's weird stuff. Anyone that deals in automotive electronics won't have any idea how RF signals can behave like that, but they do. When you point the dish at the horizon, you see the warm Earth. You see a lot of warm atmosphere, and so the noise temperature was quite high. When you pointed it up at the sky, cold sky, you get the low noise temperatures. So here's just another shot of the receive control. Now they're all a little bit different. There were different generations, and different primary stations would have had different equipment. You notice this one's got a display up here. This one's got, I'm not even sure what that is, patch panel of some sort. Just various displays. But when the station was hot, there were 4 guys sitting in those seats all the time, 24 hours a day. And so the downlink receivers. So this is when the signal comes off these parametric amplifiers, it gets down converted to 50 megahertz, filters to either 1 or 4 megahertz bandwidth. These were manual switches. The receiver operator needed to know whether to switch the bandwidth to 1 or 4 megahertz, and when to do that. And this wasn't automated. All those buttons were there for a reason on the receive control panels. There was amplification of 50 megahertz IF, which has still got all the ranging system, all the TV, all the audio, all the telemetry, all the signals are on the 50 megahertz IF. When they were receiving FM, they split off the TV at that point. The receive amplifier is not phase locked; it's receiving FM, so it's got to track the signal, but it's not phase locked with the VCO because they can't do can't do FM demodulation. They didn't use PLL demodulation of the FM signal. That's what I'm trying to say, because that would have destroyed all the subcarriers they needed as well. So then there's a further 50 megahertz AGC amplifier with about a 91 dB dynamic range. So they could actually cut the signal by 40 dB or boost it by 51 dB. The AGC was about a 10 volt DC signal, which just controlled this amplifier, multiple stages. But 50 megahertz, so you could do that with, without going to the exotica of parametric amplifiers and the like. Now, you had to down convert to 10 megahertz. The 10 megahertz and the 60 megahertz signals that they wanted all came off a 20 megahertz master crystal. So they synthesized, divide by 2 and times 3, and the 10 megahertz was used later on. I'll tell you about that. But 60 megahertz LO was used to down convert 50 down to 10, and until this point you've still got 3 receive paths because you've got the sum signal and the X and the Y. At this point you can split it off to various sources, and they had a distribution amplifiers, video amplifiers they call them, that send off in 5 different directions, off to the telemetry, off to the ranging receiver. So the telemetry receiver was a Gemini equipment, just being reused. The ranging receiver we'll talk about a bit more. It was crystal filtered at 10 megahertz with a 7 kilohertz bandwidth. Obviously, that was after the ranging had been taken off and other things, because these things had to be taken off because they had a megahertz or more bandwidth. The crystal filter was for the further into the Doppler. So then you split it into an amp and a limiter, which was for the phase detector, and an amplifier which is not limiting, to the AGC detector, which gave you the 10 volt DC AGC signal to control the earlier IF amplifier. So it was split into two ways. The phase detector for the ranging was phase detector, I think it's a 10 megahertz crystal, and again they had phase noise filters, and it was all manually switchable, and I wouldn't know which way to flick the switch, but the operators did. And they're picking off the phase shift demodulation at that point. The main VCO was a 24 megahertz VCO. This is not the crystal oscillator 20 megahertz, it's 24 megahertz VCO, which is multiplied up, multiplied up, multiplied up. It was tripled first to the Doppler extractor, and it was multiplied again by 32 to the first mixers. So that was your first down conversion. Was modified up from this 24 megahertz VCO. Any more questions about the downlink path? That's just.
What was the 7 kilohertz at 10 meg? What was that used for?
It wasn't entirely clear to me. So that was probably. It may have been used for emergency voice because that was on the centre. Not sure. That wasn't clear to me from the book when I read it. That's right. So we move on to Doppler. So the downlink, as I mentioned, was synthesised using this magic ratio, 240 on 221. So whatever the uplink frequency was, times 240 on 221, plus or minus the Doppler shift, twice the Doppler shift, because there's one Doppler shift up, one Doppler shift down, gave you the receive frequency back at the ground. And the ground receiver synthesises the anticipated receive frequency if there wasn't any Doppler happening, and it can use that to calculate the difference frequency to actually work out how big the Doppler shift is. Now Doppler shift is about 200 kilohertz plus or minus, so they actually down converted to a 1 megahertz centre. So if it's below that, the spacecraft's approaching you. If it's above 1 megahertz, then the spacecraft's moving away. And the range rate, which is not the distance away because it might be moving at an angle, the range rate was the rate at which the distance was changing, the straight line distance, disregarding the angle. The range rate continuously updates the range register. So after you've done ranging, you turn the ranger off and you update the range register with the range rate from the Doppler system. Ranging. Clearly, you've got to know exactly where you are, and you measure the range. This is the ranging system. So this actually has the ranging sequence generator and all of the correlators to figure out what you're trying to do when you're ranging is to count the number of cycles in flight. Sounds pretty easy, doesn't it? At 2.3 gigahertz, the cycles aren't very big, and they didn't have counters. We have computers that run at 2.5 gigahertz, but they didn't have transistors that ran at that speed back then, so they couldn't build counters. So the ranging sequence, you couldn't use the whole bandwidth anyway. The ranging sequence was a pseudorandom sequence sent at 992 kilobits per second, which gives you, for each bit of the sequence, about 150 meters of total accuracy. So if you can count how many 992 kilohertz waves, or cycles, if you like, if you can count how many bits are in flight of ranging code between you and the spacecraft and back again, then you know how far away it is, within 150 meters. If you can get it down to fractions of a bit, and they can actually get it down to 1 meter, theoretical, and actually down to about 15 and 20 meters. So they were measuring the number of bits in flight down to about a 20th of a bit to get 20 metres accuracy. However, if you want range out to 800,000 kilometres and you want to count the cycles, you need to have 5.5 seconds to you need to have a sequence that doesn't repeat. If you send a sequence that repeats in less than 5.5 seconds, you can't tell if they're 500,000 kilometres away or 200,000 kilometres away. It's ambiguous. Now, I think that probably would have been workable because they sort of knew where they put it. Like, if you're trying to find your car keys, you don't go and look in the place where the light's best. You go and look where you might have lost them. So if you try and look for a spacecraft, you kind of look where you think it might be. But in any case, they wanted a non-ambiguous code. And the thing is, if you're sending a 5.5 second long code, you've got to do 5.3 million correlations before you can find out which one it is. So you're talking multiple years just to get one range.
Why did it have to be 800,000 when the moon is only 500,000?
Round trip distance plus a bit of extra. Yep. And this is where somebody mentioned the Chinese number theorem. I'll get onto that on the next slide. But essentially, they used multiple different sequences that were much shorter than 5.3 million. And I'll go into how that worked. But they could choose one ranging code, correlate the number of bits in that, so they could work out the remainder. In other words, if I'm sending a 15-bit code and the best correlation comes back at being 12, then I know it's some multiple of 15 plus 12. And if I then send a 31-bit code and it says it's 23, then I know it's some number of 31 plus 23. And if I do that with the 5 different code lengths, the Chinese remainder theorem allows you to compute unambiguously the exact number of bits that are in flight. And it's a really old bit of math. It goes back to
The Chinese, for instance.
2,000 years ago. So the ranging code is demodulated and it remodulates the downlink carrier. And they have the same ranging code signals being generated with a delay. And as the received signal flies in, they fly it past the regenerated ranging code and they can slide it up and back by a certain number of bits and figure out where it locks in the best. And the codes are like CDMA codes. I don't know if anyone knows how CDMA works, but code division and multiple access. Essentially what you want is if the code is rotated out of sync, it doesn't correlate, bang, there it locks in. Okay, so the design of the exact sequence of ones and zeros that you send is done in such a way that there's an equal number of ones and zeros, because you don't want a net phase shift, because then you can't demodulate it. But you also want the pattern to be such that there's no repetition there's no shorter repetitions that correlate wrongly at the wrong rotation, if you like, of the code. Does that make sense? In the 3rd century, a Chinese guy called Sun Zi said there are certain things whose number is unknown. If we count them by 3s, we have 2 left over. By 5s, we have 3 left over. By 7s, there are 2 left over. How many things are there? Okay.
Roger?
So this is the correlation offset. This is the correlation offset for a 3-bit code. This is the correlation offset for a 7-bit code, and this is the correlation offset for whatever. So it's the same principle applying. But they use 5 codes. It turns out that because there is no number that divides into 2 and 3, or 2 and 7, or 3 and 7. In other words, there's no common factors in any of those numbers. They're relatively prime. And therefore, this will repeat every 3 times 5 times 7, which is 105. So it'll repeat. So the number is 23, but it could be 23 plus 105, could be 23 plus 210, could be 23 plus, etc. Okay, so there is still an ambiguity, but you've cut it down to from the numbers from 1 to 100, it can only be 23. And this is essentially how the Apollo system worked. The proof of an algorithm to calculate the actual number, in other words, to solve this problem generally with any set of divisors and remainders, was proved in 1247 by Qinji Shao. If you're Chinese, please correct me on my pronunciation. But this is quite old maths. And interestingly, the same maths is being used in public key encryption with RSA multiplication to do factors for signing. So every time you connect to an HTTPS site, your computer uses the Chinese remainder theorem to actually calculate and verify these signatures. So this is a really, really important bit of math. So from only 232 correlations, and bearing in mind you could be sending the 31-bit sequence while the 11 is still coming back down to you, so they can overlap the correlations. The 2 was kind of implicit in the modulation of the system itself. So 11, 31, 63 and 127 were the alternate codes that were set. And this resolves the required 5.3 million bits from just 232 correlations, which means I could actually get a range fix in a few seconds. After getting acquisition of signal, they could turn on the ranging codes, it would go through the various correlations, send the different ranging codes, do the correlations, calculate the maths and figure out how far away the spacecraft is. And then the fractional cycles on the correlator, because it was sliding continuously, gave them down to theoretically 1 metre range, ambiguity, out to 400,000 kilometres. And practically they achieved about 15 and 20 metres range accuracy, which is spectacular. So anyway, and I found the guys explained this stuff to me while I was down in Canberra. So they're still, in their 70s, they still remember this stuff. You know, several people quoted these numbers to me from 50 years ago. So it was very deeply ingrained. There's the ranging receiver here. Time processing unit there. You can see the receive controllers. This is antenna steering. This guy's looking out the window. Well, he's not looking out the window now, but...
This fellow on the left-hand side is obviously just discovered a problem.
He's taking a photograph.
That's, yeah, the telemetry data processor and stuff is in there, so that's repurposed Gemini designs.
We have a problem.
But there were computers the other side of that wall. They actually ripped out these partitions and joined some of the rooms together. The equipment was always being upgraded, so these designs are, I mean, even the PDFs I got this information from, some of it was out of date for Apollo 11, some of it had already been updated before then, but you get in the basic picture. There's paper recorders, chart recorders and things you can see running here. I forget if I've got a slide on the time standards. I'll talk about time standards when we get to it. But this is at Goldstone. So again, you can see the 4 receiver channels, the exciter control panels over here. I forget what these are. And again, they've got antenna steering over by the window. This is Bill Wood supervising a team. So they had 12 guys operating the station anytime it was live. 4 of them operating the receiver exciter. 12 people. 1 operating the power amplifier, 1 doing ranging timing, 1 doing antenna work. You can't see the antenna guy, he should be on that seat there. 2 signal data demodulation, so these boxes behind here would have 2 guys working, making sure that everything is operating and switching over to backup if needed.
Where's the equal opportunity employment?
You know what? Some of the women did some of the most important tasks in this whole thing. They were not in operating these, but actually doing the maths. Like they didn't know until the 60s, if you brought a spacecraft in at a certain angle, what curve it would follow to splashdown. They didn't know that. That was solved by a woman.
We saw the movie, but
Good movie. What was the lady's name?
Yeah, black woman. I've got a picture of her and her equation somewhere.
Figures.
Yeah, that's a great book. Yeah. The women were the computers, and then they took up programming the UNIVACs, and the computers were the computers, but the women were the computer programmers. But they employed a lot of women to actually crunch the numbers, because in the early days, all the burn times and all the trajectories and stuff was all done with hand calculation.
Did they ever allow for the angle in the ranging thing at all?
Well,
So we line of sight.
they knew what the mass of the moon and sun and the orbital paths were.
I suppose they know the velocity.
So whatever, and they had direction. The big dishes could give them quite accurate direction, like 0.1 degree beam width, but that's still quite a lot of kilometres. So they had to actually figure some things from other things that they knew before. You know what I mean? So if you knew it had gone in 70 kilometres above the moon on one side at a certain speed, it was going to come out a certain distance on the other side. If that was wrong, you could correct your orbital estimate by a certain amount. So they had all the deltas pre-calculated. You know, we're going to aim for that. If it comes out like that, we know we're on the money. If it's a bit left, then we know it was a bit, etc. So you see what I'm saying? One thing corrects another, and they had that. So there's a massive amount of calculation involved. And although they did have a lot of UNIVAC computers, I think there were 2 in each of the primary stations, and a lot of them were doing data processing for sending stuff up, telemetry links and stuff too, into Canberra and across to NASA. So the up data, there are multiple things that you can tell. You can send real-time commands, which were a fairly small number of codes, 6-bit codes. 6 were the address saying which device am I talking to, and 6 was the command. The guidance and navigational computer, which you could send things like, at this time, do this burn, was a 22-bit code, and the central time equipment needed quite high bit lengths. So the UNIVAC computers were 30-bit computers, so that was a full word. And they all had to be, the Saturn V booster, by the way, the stage 3 booster also had S-band and UHF, and it was also had to be tracked because it was out there in space. And with Apollo 13, they had issues because they needed to talk to the modules separately, but they were on the same frequencies because they were meant to have already crash landed the LEM on the moon, and they couldn't talk to the command module. They couldn't talk to the LEM because the command module was grabbing that same frequency, so they had to lock onto. And there was actually Australians who figured out a way of solving that problem because they'd actually workshopped a case like that and practiced it with aircraft flying past, and they were tracking these aircraft, and they practiced talking to 2 receivers and pulling the signals apart. They'd turn one receiver off, lock onto the other one, throb the transmit frequency to pull it away from the centre, then they'd turn the other receiver on, turn another transmitter on, lock onto the second receiver and pull it the other direction. And they'd stay locked on. As long as they stayed locked on, they didn't, as soon as they lost lock, they'd snap together back to the middle again. They have to lock on, turn one off, lock on again, pull it apart. So Apollo 13, they had to actually apply that. It's a great story about it, but it wasn't in the film, unfortunately. It was sort of vaguely mentioned, but it was a really interesting thing. So it was only a 1,000 bit per second data, phase shift key modulating a 2 kilohertz oscillator. That went onto a 70 kilohertz subcarrier with a 5 kilohertz deviation on S-band. On UHF, it was directly modulating the UHF uplink. They used BC error correcting. I've actually implemented BCH, which is something similar, but basically they wanted to make sure that a command that was received wouldn't be rejected, would be falsely rejected being a good command in 1 in 1,000 cases, but they wanted the false accept, like fire the engines now, in 1 in a billion. So the error correcting codes that were built around these commands that were sent up were computed to be sufficiently powerful to correct X number of bit errors with probability, as given. Correct or detect errors. So they didn't want to think it had been told to fire the engine now when it was actually being told to turn on the cooling. The telemetry used a wideband amplifier and a biphase detector. I mentioned that was a Gemini carrier, and on the subcarrier there was a NRZ pulse code modulation. Again, because they didn't know how much signal strength they're going to have, they had switchable data rates. So they could, if they weren't achieving 51 kilobits per second, they could switch things down to 1.6. And throughout the Apollo thing, they have this back-off thing, right back to emergency voice or emergency key. They have these back-off modes where if it didn't work at the high rate, they didn't actually use 200k, they used 51, I believe, on Apollo 11. But anyway, they had these back-off frequencies. Oh, that's another... This is the antenna steering, I think. Sorry, I had information about what that was, but... so on the spacecraft, both the command service module and the lunar excursion module had omni antennas. On the LEM, it was just 2 spirals because it was only a fairly small thing. On the command service module, they had 2 on opposite sides and then 2 at 90 degrees, which were, I think, just dipoles. Maybe not. No, they were omnis. I'm not sure how they did it on the CSM. Bottom line being that as the spacecraft shifts, you can still hear it because one antenna might be around the back of the spacecraft. You've got to be able to hear the other one. They both had a high gain steerable antenna. They were different, quite different antennas, but and on the LEM they also carried the umbrella that you see Armstrong erecting on the moon to send TV signals back directly from the lunar surface. So there was a long cable to the camera, another cable that came out to the antenna, and that's how we got to watch the TV. Oh no, not the TV. That's how we got to watch the subsequent pictures. I mentioned the phase locking. The command service module had a travelling wave tube. I didn't know the word amplitron before, but the LEM used an amplitron. It's kind of like a travelling wave tube again. You launch electrons down a thing, and it modulates and gets sucked off a port. I don't really know how they work, but if you look at Wikipedia for travelling wave tube or amplitron, you'll find out all the details. They both had about 20 watts in transmit. So not a lot of power because they only had to run off batteries, right? Only the CSM could take up data commands. So the LEM they couldn't remote control the LEM. It had to be done by voice command, and the astronaut would actually do what they were told. And again, the CSM supported record and replay. It had tape recorders in it that could replay voice and telemetry. So that was actually what was on the... Oh, and again, the high gain antennas were steerable, and they had auto steering on them. So when Armstrong's trying to land the LEM, he didn't have to worry about where the antenna was pointing; it was steering itself. So again, they had to have the some X and Y channels, do all the differencing of signal strengths, and figure out how to automatically steer the antenna. The ships had a wide variety of things. Up the top here you can see log periodics. The next antenna is a UHF telemetry antenna, so they could talk to satellites and stuff with that. The unified S-band antenna is the 9 metre dish there, which has got the little 1 metre acquisition aid in the middle of it. There's a Star Tracker dome in here, which is used for locating the ship itself and position accurately. C-band antenna, which is the radar, so it's a 6 or 8 gigahertz radar for figuring out where something is in orbit, how far away it is. There's a SATCOM terminal antenna, and there's HF whips, control command antenna. So
Presumably the dishes had gyro stabilisation in case there's a big sea.
they must have had, and actually when you get to the Orion aircraft, these aircraft could lock onto something there, and as the aircraft's being buffeted about, it was all gyro stabilised and balanced so that it was automatically locking on signals. So they were built on C-135s, which is like a shorter, thinner version of a 707. I've got a picture of them in a minute. They were called the Snoopies because of I'll show you the picture. You can see why they might have been called Snoopies. Some more pictures in a minute. But so they were... they had S-band, but they were really only concerned with orbital or near orbit. And in particular, they were important for finding the spacecraft after it came through the blackout period during re-entry, when everything's too hot and you can't hear anything anyway, too much thermal noise. So they'd have a couple of minutes and they'd lose track of the spacecraft completely. And the aircraft are buzzing around saying, we think it's going to come in there, and they're hanging around out at the edge, pointing their dishes, they're searching to try and see when the signal reappears. And when they'd find it, they'd quickly lock onto it. And okay, acquisition of signal, we know where they are. It's going to land there. Get your helicopters out there and pick them up. So they had to have ships nearby as well, of course. But they could get those anywhere on Earth. And in fact, with Apollo 13, they had to get them into the Indian Ocean because they... Oh no, that wasn't right. They planned to get them in the Indian Ocean. They wound up actually being able to correct it and bring it into the Pacific. But on an earlier part of the Apollo 13 orbit, they thought they were going to... From the burn from behind the moon, they thought they were going to actually land in the Indian Ocean. And then they did a 14.3 second burn and corrected the path, and that was a manual burn. But these RI aircraft had to be able to get anywhere on Earth with their ship support, and because they were quite high, 35,000 feet, you can see a lot further because the horizon's a long way away. So they had quite good range, better than most of the terrestrial stations had. They could go 80 degrees left or right, 80 degrees up, and I think about 20 degrees down. Obviously no point looking at the ground because you only hear noise from the temperature of the ground. They had HF links to the ground stations, and they had a 100-watt S-band transmitter and no ranging. But they were running up to 10 simultaneous VHF links. Now you can't see, you can see the mounting here on the side. So this is pivoting, and there's a mounting above that pivots this whole thing. The whole fork would pivot like that, very, very quickly, gyro-stabilised, high. The UHF antennas, which are normally mounted on these 4 points, have been taken off on this one. You see them on this. So these are used for acquisition. So because they had a much broader beam width, like a 10-degree beam width from that dish, they could use those to find out where the signal was and point it in the right direction, and then the S-band would lock in. This is Stan Anderson. So a photo I took of him when we were down at the weekend in July. But there again is you can see the mounting of the dish in the nose of the plane. So that's my coverage. Most of the information came from this book, or from Colin McKellar's site, honeysucklecreek.net. A lot of good stuff there, heaps of photos, quite a few good stories. And Colin's a wonderful guy. He lives out in Western Sydney. He's actually a priest. But he's had a lifelong passion for the Apollo stuff and has written it all up. And in fact, he scanned this book to the PDF, and some of his stories and stuff have been manually verified by the astronauts involved in the missions and stuff. So very well connected.
Any questions? I mean, that's all very high tech and way over my head, but all this technology, all this new, all this smart stuff, did that exist during that time? Was that known, or did they have to develop new methods or?
There were new methods. I mean, they used stuff that had been developed in various places, and they brought it all together.
Right.
I mean, and bring it all together in the way they did with this was a new thing.
Yeah.
So Unified S-band was new for Apollo,
Yeah.
but the telemetry, for example, had been used on Gemini. The ranging system was something that JPL had worked on. So there were different things that, they had C-band radar. They had because they'd been doing, tracking of orbital missions for a decade or more by then. So there was quite a lot of different technologies they drew from, but bringing it all together in this way was a massive expansion. And obviously training, you can see how much equipment they had, because everything's multiply redundant, and they've got to have places all around the Earth that have got this equipment. They've got to have people that know how to operate, and they've got to have people that operate while those people are sleeping. So they had quite large teams. There's a couple of hundred people. It's not like The Dish, the film, where you see two sheep farmers who've been trained to push the right button when they're told to. It was, the guys at Honeysuckle, I worked with Rob Day, who was there from Apollo 13 on. He was at Hewlett Packard in the 1980s, and he was quite offended when the dish came out because of how he realised it was a populist thing. It was meant to, make it attractive to people to go and see the cinema, go and watch the film. And in most of the factual elements, it was correct, but it just didn't show the level of technical skill that was required.
tubes.
Oh, the ditch.
Yeah, Rob was actually standing behind one of those receivers when the guy said, Houston, we've got a problem, we've got an undervolt on main bus B. He was actually standing behind the receiver that received that signal. So when Apollo 13 reported and he's a young guy, just out of university. So
if they were doing it today, they'd obviously do it, well, not exactly differently, but it'd be a lot easier to do it.
well, you wouldn't have to use tubes for everything.
Yeah.
I mean, you might have tubes for your multi-kilowatt PAs, but you can imagine how much gain they need to be able to get out to Voyager out in the Kuiper belt, out past Pluto. I mean, they've got big dishes and they've got megawatts going up the spout, and they're only just being able to get, seconds per bit, not bits per second.
We've always got to have balance.
And of course, Clifford, you've actually come up with two things. You've come up with something that can be used with Morse code with JOTA, and the ultimate trivia quiz question, which is, what did the Titanic and the command module have in common? So that'll be a good one for the scouts.
Very good.
I usually use the Titanic as a what use was Morse code and where was it? What's the most famous use of it? And they all sit there rubbing their heads and you say that's a ship, and I go, oh, the Titanic, because I've all heard of the Titanic. So there you go. Well, thank you very much. That was an excellent. I must admit, when we got to the Chinese theorem, the bit was, what do we have left over, and it all turned into blah 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 after that. But apart from that, it was very good.
Must have been a great moment for you to be down in Canberra.
Well, I heard about it because I asked Rob. I sent Rob Day an email and said, what's happening? It's 50th anniversary coming up. What are you guys doing?
Yeah.
He goes, we're getting together in Canberra and everyone's invited. And I sent a message out to the Manly-Warringah list, and Ian Schwalk actually went down, and a cousin of mine went down as well. So, and Ian dragged one of his friends from Wollongong across as well. So there were 4 of us there. But there were 400, 500 people at the main dinner. But we had 4 days of activities. Like for $70 we paid for the lunch. We were being bussed out to Honeysuckle Creek.
It's not the $70 that's convincing the wife it would be a good idea.
Anyway, it was just...
Violin out, right?
It was a magic thing to do, yeah. And it was the last time those guys are going to be all together again.
Oh,
Just one comment. Both Shardry code, the error corrected code.
Yep.
Interesting. This is in the 80s. All the SCADA systems use that code.
Okay.
You're tripping a generator out. All the controls going out with both Shardry error correction.
Interesting.
Yeah, so we're using that now in the 80s on all the SCADA. So just about, let's say, any generator in New South Wales, the operator sends a control out. It uses both.
So I used BCH codes,
Yeah.
but on a project which gave rise to the geekiest sentence I've ever said in my life, which is actually true. Someone was talking about use of GNU plot to show plots. I said, I've used GNU plot to show RF impedance spectrograms from nanotech RFID devices. And because this company down in Melbourne is building these miniature, not RFID, actually they're mechanical resonators inside a millimetre cube chip with a little antenna on it. And we ping these things and you get resonances from the resonators internally that aren't damped, and you get like a musical chord. And I wrote software and it was BCH error corrected on that to actually, because the chords all move around, but it was an ID system essentially for biometric cryogenic storage, for biological sample storage.
You don't have any pictures of the plumbing used that are very high frequency?
Not from the Apollo stuff, no. But if you Google for Magic T hybrid, you'll find a good picture of it. It's got 2 flat ports like that, 1 flat port like that, another one that's that way, rectangular in that direction, pokes off the top. And it has a weird effect that if you feed 2 signals in here, the sum comes out there and the difference comes out there, or something like that. And that's what they used in the feed horns, a ring of these things to add up and subtract all the things to get the right.
Something to do with the E and the H fields.
That's right.
The right phase. And
Yeah, that's it.
subtract,
And if they're made accurately enough, you get very accurate addition and subtraction. So, yeah, magic stuff.
Fantastic.
Good, oh.
So, Rod, before we go, we we need to talk about this, anybody who hasn't signed up for the dinner.
Oh, yeah, so there's